Then it's my pleasure to welcome Tony for one of the last talks of this conference. Well, that's it.
Okay, thank you very much. So I sorry I didn't pay attention. I was checking the web page, and of course it was announced this morning that my talk was 4:30, but I don't know why. I was checking web page. It was written 5, and I was there. So it's a bit later than was planned, but here we are. Thanks for being there, and of course, thanks for. I want to thank the organizers for inviting me to give a talk in this nice conference. I was in the previous one in Sao Carlos. It's always a very nice event where. I'm sorry I couldn't attend more because I was with a meeting here during the first 2 days, but I enjoyed many of the talks. And so the purpose of my talk is to give you a sort of overview about a series of works that we had in my group. I mean, this is not a... We started working on non-Markovian dynamics, and then we got several results in this direction on the characterization of non-Markovian dynamics. And my talk is going to be about these results. I'm going to present these results, which somehow aim at understanding whether any non-Markovian dynamics, in a sense I will define later, always has an information backflow in a sense that I will also define later. Okay, so the goal is to make connections between these two concepts. And there are several people involved in this, in the works I'm going to tell you about. So there is, I mean, in all the projects we have Bogna and Marcus. They were postdocs in my group. Now they both left. And in the last part, the last 2 projects, there is Dario, who is a PhD now in the group, and there is Naja, who is a professor in Recife, who was here, but she left right after, before my talk. Okay, she didn't want to see me, given the explaining the results. Okay, so this is the, well, I have some introductory slides about the topic so that we are more or less all on the same, we all understand what I'm talking about. And so I'm going to consider an open system dynamics. So there is a system and there is an environment. There is a joint evolution of the two things, of the two systems. And I will mostly care about what happens to the system during the evolution. So as you may know, so the evolution of the system is given by the joint evolution of system plus environment described by a unitary operation. And this acts on the system and the state of the environment. Usually they are taken at the initial state as uncorrelated. And then you trace the environment, and this defines the operation on the initial system. And this is some of the main object of my talk, and defines a quantum channel, okay, acting on the initial system and defining the evolution of the system with time. So the dynamics is described by this set of channels or maps, lambda t, okay? And this is a continuous set. So the evolution is described by all these different channels during the evolution, and this is often called dynamical map. So, okay, I have a disclaimer. So I must say that I'm not an expert on open system dynamics. I'm starting, okay? So you have any comments? Of course, they are very welcome. If I forget any reference or anything like this, please let me know. Okay, so just a few definitions. So as I say, this is the main object during my talk, and well, these are just definitions that exist. So a map is positive. One of these maps, whenever it maps positive operators into positive operators. Okay, so if I can define a map, which is an object that maps operators into operators, and I would say that a map is positive whenever any positive operator is mapped into a positive operator. So in principle, this maps any physical state into a physical state when it's trace preserving. But we know that for a map to be physical, it has to be positive, but actually it has to be completely positive, because we also want the map to behave in the right way also when acting on parts of a subsystem. Okay, so it's not only that the map has to map positive states into a positive state, but it also has to do that when acting on parts of a system. And this is the definition of completely positivity. So a map is completely positive whenever the map tensor with doing nothing is positive. And actually there are maps that are positive but not completely positive, and I guess it will happen during my talk that I will sometimes use the definition of positivity to mean something that is P positive but not CP. Okay. And as I say, physical channels correspond to completely positive trace preserving maps. I guess many of you know these things. And then the map the dynamical map, which is the object that describes the evolution, is said to be P or CP or just divisible whenever for any two maps with time t larger than s, one asks that the map lambda t can be expressed as the map up to point s plus another map from s to t. So whenever this happens, I would say that it's divisible. Whenever this map V is positive, I would say that it's P divisible. And whenever this map V is completely positive, I would say that the map is CP divisible. Okay. And in most of my talks, I'm going to focus on invertible maps, bijective evolutions. And these, by definition, they are divisible because this map here cannot be written as, if you have the state at evolution S, you can go backwards in time and then evolve up to time t. And you can always play this. So you can always define this map, then the dynamical map is for sure divisible. The question is whether this is P or CP. Well, just to give an example that I'm going to use also during my talk, there is a map that to my knowledge was studied in this paper, and it's just, this is the Liouvillean of the map, and these are just Pauli matrices acting on the state rho, and we have some coefficients gamma, and playing with these coefficients, you can make the map to be CP or P. Okay, this is not so important. What I'm saying is that there are some examples where we know this definition, so you can take, whenever these coefficients here are positive, the dynamical map is CP divisible. Whenever the sum of any pairwise combination of the coefficients is positive, it's P divisible. So you can see here an example you can construct by tuning these parameters, for instance, an evolution that is P but not CP divisible. And this is an example that we are going to use as well. So if you take this definition that defines through the Liouvillean map, and I take alpha positive, I can take this map, and you see here, whenever you take the sum of two coefficients, okay, you will have either 1 plus 1 or 1 minus the hyperbolic tangent. This is always positive, so the evolution will be P divisible. But if you take t larger than t0, this becomes negative, so the evolution is not CP divisible. So this is a situation where I have a map that these people introduce, where I can play between P divisibility and CP divisibility. And something that is going to be useful for the rest of my talk is that I can choose this t0 at wish. So in particular, I can move this t0 arbitrarily large in time. So I can play with this evolution so that the evolution is CP, okay? And then it happens to become not CP whenever I want by just tuning this t0. Okay, this is going to be useful for what follows. Okay, so just remember this. We can postpone the failure of CP divisibility at wish. I can just, by choosing t0 large enough, I can move it very late in time. In particular, I can move it arbitrarily close to the stationary state of this evolution. Okay, so I was defining the maps. This is going to be my object. Now I will define non-Markovian dynamics. Well, there are very definitions. Actually, one of my motivations to study this is that I was attending some conferences on non-Markovian dynamics, and everyone had his own or her own definition of non-Markovianity. Okay, so it was a bit like, okay, what is going on here? So whenever I'm going to say non-Markovian dynamics, I'm going to refer to CP divisibility, which is sometimes used as definition. So for me, non-Markovian dynamics, I will mean something that is not CP divisible. And I think this is nice formally because it somehow reflects a notion of absence of memory. I mean, usually non-Markovian dynamics are also Markovian dynamics are usually described with the notion that the evolution at time t plus 1 only depends on the state at t, and you have to keep track of the previous memory. And you can see that whenever something is CP divisible, so this is the map lambda s up to point s, and somehow you could, in principle, throw away the environment, prepare something new, and run the new map from s to t, because there is a physical channel for that. Okay, so this encapsulates this notion. It's a possible definition, which makes sense, and I'm going to adopt this for my talk, okay? Because, for instance, also classically, you have this notion of Markovian process. Okay, so this is, I introduced the channels, I introduced the definition of Markovianity that I'm going to use, and now the other ingredient is, I would say, a bit more operational. So people also tend to associate Markovianity, non-Markovianity with backflows of information. So there is the environment who somehow gives a backflow of information, and somehow intuitively we tend to associate non-Markovian effects to information backflows from the environment to the system. So how to formalize that? Okay, this is what I'm going to do. I mean, people have done this in the past. So usually what people do, they take operational quantities, you name it, you take any quantity that you like, that are non-increasing under the action of a channel. Okay, there are many, there are several quantities that do not increase under processing. Okay? So you can take those channels and follow those quantities and follow their evolution after applying the dynamical map. And we know that if the dynamical map is Markovian, is CP divisible, well, it's like you are applying a map all the time. So these quantities should decrease, 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 decrease because they are monotonic. Okay? So if at some point you see an increase of this quantity, well, this is an information backflow coming back from the environment, and you detect this as non-Markovianity. Okay? This is also, I guess many of you know this. Okay? So you monitor the evolution of this quantity, you know that it's monotonic. So if it's Markovian, it's like if you were applying a map, so it should decrease. But it may happen, in some cases it happens that this quantity increases at some point, so this is a signature of non-Markovianity. So just examples that were introduced. I think one of the first papers considering these things was by Breuer, Leine, and Pilo. So they said, okay, why don't we study the distinguishability of two states, the distance between the two states. So we know that the distance between two states cannot increase under post-processing. So you apply you have two states, and they have a given distinguishability. You apply a channel to the two states, they become closer. So they become less distinguishable. And a natural notion of distinguishability is given by the error probability. So if you have to distinguish between the two states, what's the probability that you make an error? This is given by this function. And this is the trace distance between the two states, and well, this is also called as distinguishability. And we know that this increases when you apply an operation. So this means that this decreases. Okay, so the error increases, and because of this sign, this decreases. Okay, so this is either you take the error probability of this distinguishability. This is something that is monotonic with evolution. Okay, so if you see, you follow the error probability of this distinguishability with evolution, and you see that this is violated, then there was a non-Markovian effect there. But of course, this is the original definition, but you can do the same. I mean, if you have an ensemble of states, so here it's like you are given two states with probability 1/2, but if I give you two states with probability p and 1 minus p, well, the same logic applies, okay? So the error probability, again, is increasing, or if you want, this distinguishability is decreasing, and actually what happens is that you only have to replace here, you had some 1/2, so you have to replace by p and 1 minus p, and you have the same argument, and this may help in some situations. Or why should you restrict your considerations to two states? I think it makes more sense, like you have an ensemble of states, and again, you can prove, so you give you an ensemble of different states, rho I with probability pi, you can see that the guessing probability, that quantifies what's the optimal probability of guessing correctly the state you are given, is also monotonic under channels. Okay, so that this was considered in this paper by Buscemi and Data. Okay, so this is one thing based on distinguishability. You follow the distinguishability between states in an ensemble. And for instance, another approach that has been proposed is like you monitor the correlations of your system with an additional particle that does not follow the evolution. So we also know that if I follow the evolutions between these two particles, also correlations do not increase by local operations. Okay, it's not entanglement, it's just correlations. Okay, so I'm not saying, I just apply a channel here. For sure, correlations cannot increase by doing local operations. And my correlations with Marcello cannot increase by me doing stuff here. And this is what I demand. So it should happen that if an evolution is Markovian, then correlations cannot increase. Okay, so this has been proposed, and people actually use as measure of correlations. Actually, in this paper, the authors proposed to use entanglement, which is also a notion of correlations, okay, as a quantifier for a detector of non-Markovianity. And also in this paper, some other authors proposed the use of mutual information. Well, again, any notion of correlations in principle should work for this task. Okay, so that was a context for my talk. So what I'm going to do, well, I want to see how non-Markovianity understood as non-CP divisibility corresponds to information backflows. And as I was telling you all the time, if things are CP divisible, you can take it as a constant application of a channel, and then because of this monotonicity, this you don't have any. Wait, it should be no distinguishability backflow and no correlation backflow, a typo. Okay, so whenever you have CP divisibility, it implies that these things They don't show any backflow. So what I want to know is whether this is an if and only if condition. This is basically. So if any non-CP divisibility corresponds to a backflow for distinguishability of correlation. Now let's start by distinguishability. There was some results on that. So the first thing is like there was a result by Kosakowski who proved that if a map is positive, then it is contractive on the trace norm. So it means that you have an operator X and you compute the trace norm, then if you apply a map that is positive, this becomes smaller. This is a mathematical result, if and only if. But now this happens, this implies that for bijective maps, so things where you can invert, you can always see a backflow of distinguishability between two quantum states, okay, whenever things are not CP. Okay, for you to understand why this happened is because if you have the map V, okay, this is the map that goes from S to T and is not positive or CP is not positive, then there exists this state that whose trace norm increases. Remember that this trace norm was related to the distinguishability, okay? So you can see that you can interpret, this is easy, I'm not going to do it, but you can interpret any operator X as a distinguishability between two states with different probabilities. So basically what you take these operators, and you can write any operator as a positive par minus another positive operators. Okay, so you make this composition. So you reinterpret this operator here, given this failure, as an ensemble of two states. And then it follows. Okay, this tells you that whenever the map is not P divisible, you have an increase of distinguishability of these two states. Now, if you want to extend it to CP, you play the same trick, but now you replace this lambda by identity tensor lambda. If it's not CP divisible, identity tensor lambda is not P, and then you can apply this, but now these two states are correlated states between system and ancilla. Okay, so it's just the same logic. And for the case of even non-bijective, okay, this applies for invertible evolutions because you should define this object V of ST. When the evolutions are non-bijective, Buscemian data prove that there always exists an ensemble showing the backflow of distinguishability. Okay, what we didn't like so much here is that none of these results is constructive. Okay, so here we know that it is an X, but we don't know where to find this X. Okay, and in this case, it's even, I think we know even less. Okay, so Buscemian data, what they prove is that there is an example where you will see the increase in the distinguishability. So this is what we did in this paper. So we gave a very simple example, a very simple construction for detecting the information backflow of non-Markovian dynamics in terms of distinguishability. So I will tell you about this method. Usually I don't explain many technical results in my talk, but I think this is relatively simple. We'll see how it goes. Okay, so remember, I'm going to do it only for, we only know how to do it for invertible evolutions, okay? So this object exists, or divisible, okay? So this object exists and tries to explain the evolution from S to T. Now I'm going to assume that this is not CP because I'm assuming that the evolution is not CP divisible, okay? So this in particular means, I guess you know the Choja-Minkowski isomorphism. This means that this map acting on a maximal entangled state is not positive. Okay. So now what you can see, I do the following. I take this operator, and now I act with this operator onto any state you like, rho A, and tensor with another state D plus 1. So this is a maximal entangled state up to dimension D, and I add one extra degree of freedom of dimension D plus 1. And now it's just a one-line calculation to see that the trace norm of this state is larger than the trace norm of the initial operator given by the difference of these two states. And why is it so? It's just simply because this is negative. Okay, so you have to believe me. Maybe you already see it. If not, it's easy to see. And since this state is orthogonal to this state, because D plus 1 is orthogonal to all the maximum entangled state, this number is equal to 2. Okay, so you can easily see that this is a violation of this contraction that I can interpret as distinguishability between a maximal entangled state and this state. Okay, so this is the initial distinguishability, and this is the distinguishability after the application of the maps, and I would violate this. well, this is an academic result. It cannot happen because you are never going to have this state in the image of your evolution, because if that was the case, then you would have a negative state, okay? Because this is the evolution from S to T, but this state will never appear at time S, because if it was the case, then the state at time T would be negative. Okay, so this state may not be, well, actually it's not in the image of a non-CP divisible evolution, okay? Because if it was like I was having the state phi plus at the moment where the evolution is not CP, it would mean that this evolution would produce a negative state. Okay, this is not a problem. We can play with this. So this is a state where you could, in principle, see a violation of distinguishability, but you cannot because these states are not in the image. So what you do now, you take a state in the image and you mix with these two states so that the mixture is in the image. You can always do that for bijective evolution. So you take a point in the interior of the image, you mix him, and you choose this P at wish so that it enters the image of the channel. Okay, so this is the image of channel at time S, and I want to see the backflow at time T because the channel is not CP divisible from time S to time T. So these are the two states at time S that are in the image at time S, and that will give a backflow of distinguishability at time T. Okay, so, and you can see, again, this is very simple, that if you repeat the same calculation as before by these two states, when you compute the difference, these terms, this noisy term that you add just to put the states in the image disappear. So you have everything multiplied by P. So you have the same calculation as before. It's just simply that everything is multiplied by P, but it's just an inequality that you multiply by P, so the inequality is still violated. Well, I'm not sure if everything was clear. I hope it was, okay, but maybe not. Okay, so what I'm saying is that because of Chodzia-Miałkowski, it's very easy to see a failure of contraction, and playing with this P noise factor, you can put the states into the image, and then the construction follows. So these are the states at time S that will show an increase of distinguishability, and now to find the initial state, you only have to map these states back because the evolution is invertible, and this gives you the two states that you have to put into the channel, and these two states you will follow the evolution, the distinguishability will decrease, 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 and from time S to T, it will increase. Okay, the nice things about having constructions is that you learn from these constructions. So what we know, for instance, here is that because of that, I can always do it with two states, with the simplest example you can think of. Okay, so the simplest ensemble of states is enough to detect the failure of CP divisibility for bijective evolutions. Okay, so two equiprobable states are sufficient. The only thing I had to do with the construction is to have an ancillary system of dimension d plus 1. Well, okay, I think this is not, I don't see any fundamental problem with this. I think the first surprise to me was that the argument I was telling you, it's valid for any value of P. So in particular, I can take a P arbitrarily close to 0, so the two states are arbitrarily close to each other. So I don't need any initial distinguishability to see a backflow. I can give you two states that are as close as I want, and these states will evolve and will show an increase of distinguishability when the evolution is not CP. Okay, so this is because, and actually this is a family of states. I can give you many states satisfying this property, but in particular I can give you two states that are arbitrarily close to one to another. And also, I tend to, before starting this, I was thinking that, remember, I want to see even evolutions that are P divisible but not CP, so you have to add an ancilla to see the failure of distinguishability. I thought that you had to use entanglement, but actually you don't need to use any entanglement. So with this P, since you can make it arbitrarily small, these two states can be separable. And still you will see, with two separable arbitrarily closed states, you will see an increase of distinguishability. Okay, so that was for distinguishability. So somehow we managed for bijective evolution to see any CP divisibility corresponds to a backflow of distinguishability. So the second object was, let's now try to see what happens for correlation measures. Okay, and this is what we study here, and we have a second paper in preparation where we have many results in this study. Okay. So what is a correlation measure? Again, I want to monitor the correlations between two particles, one progressing with evolution, and the other one that does not go through the evolution. So, and I want to study correlations. Well, here, again, you can be mutual information, entanglement. I think we have to be general. We will consider any possible correlation measure, And what is a correlation measure? Is something that does not increase under local operations. So I will demand from my function that is something that does not increase under local operations. Okay, this is, I would say something is a correlation measure whenever this is satisfied. Okay, I think we don't need to spend some time on that, but you can prove that basically this correlation measure is easy to make it positive and 0 only for product states. But what are examples of correlation measures? Of course, entanglement is an example of correlation measures because entanglement on the state rho AB does not increase under local operation. Actually, it does not increase even if you use classical communication. But for what matters, it does not increase under local operations. And the mutual information is also known to be contractive under local operations. So the mutual information does not increase under local operations. Again, any function that satisfies this, I think, in my view, is a proper correlation measure. And any function that defines this property is enough to detect correlation backflow because you only demand monotonicity for maps. Okay, now let's see if entanglement works whenever you have a non-Markovian dynamics. Well, it's relatively easy to see that it cannot be the case. We have some examples. Okay, I will try to explain you what's going on here because I see that the definition is not so good. So we have some explicit examples of what I'm going to tell you about. So take an evolution that somehow becomes noisy. Now you have a map that is introducing noise into the system. You follow the evolution, say, of a initial maximal entangled state. Okay, so the entanglement in the state is deteriorated. And now you can make so that the evolution becomes at some point entanglement breaking. So the state enters the separable ball. So the set of separable states, and remains there. You can do that. And now you tune so that the non-Markovian effects, the failure of CP divisibility, happens once the state is within the set of separable states. Well, this is trivial, okay? I'm sorry. Yes, I know. This proves that you cannot have, entanglement cannot detect any failure of CP divisibility because all failure of CP divisibility is in this region and the entanglement measure is 0. Okay, so it's trivial. I'm not saying that it is super deep, but it shows that it fails. Okay, and we have channels satisfying these properties. Okay, so this is a time where it becomes entanglement breaking. Okay, and you just remain there, and let's say this is where non-Markovianity appears. Well, entanglement will remain 0 all the time. Okay, for the mutual information, it was much harder. Actually, we proved that mutual information also fails, but it was much harder. So, for instance, something that we try to prove that it may work, or maybe. So we were considering this question. We say, why don't we prove that the best state you can have is the maximal entangled state to see a backflow of mutual information. And actually, we saw that there are situations where this is not the case. So I can give you examples of dynamical maps where if you inject the maximal entangled state, mutual information decreases. But if you inject a partial entangled state, you have a backflow of mutual information. And this makes the problem difficult because you have to prove that for any initial state, mutual information, whether it shows or doesn't show a backflow. So we could prove it, but then the proof was a bit more complicated than that, but I will give you the intuition, okay? So let's assume you are interested only on backflow of a quantity or properties of a quantity near a stationary state. So if you go near to the stationary state, you can make a perturbative analysis around the stationary state to see how the quantity behaves near the stationary state. So what we did was, in particular, if you remember what I was telling you, we have an evolution where by playing with a parameter, I can put all the non-Markovian effects very close to the stationary state. Okay? So it happens that for some of these evolutions, so I can put all the non-Markovianity as close as I want to the stationary state. And it happens that for these evolutions, for some cases, we made a perturbative analysis of the mutual information near the stationary state, and we can see that it does not increase at some point. Okay, so we have evolutions where we can prove that near the stationary state the mutual information does not increase, and I can even move the failure of CP divisibility as close as I want to the stationary state, so it follows. Okay, so these are very lengthy calculations that mostly Marcus did, but it proves that this fails. Okay, so entanglement fails, mutual information fails, so we were wondering, is it possible to find any correlation measure that detects a backflow for non-CP divisible evolutions? And somehow we found one, okay, that was new, that detects all any failure of CP divisibility. Okay, and this is what I'm going to tell you about. And for that, we had to be creative and invent this correlation measure. So for that, I will require some ingredients. So the first ingredient is something that I call a maximally entropic measurement, or maximally entropic POVM. It is defined for a given state. Okay, so I would say that the measurement is maximally entropic for a given state whenever this measurement this n-alco measurement acting on the state, rho, gives a fully random output. Okay, so the probability of getting any of the n possible outputs is equal to 1 over n. 1 over n, okay? So it makes sense, okay? It's a maximally entropic POVM because you produce a fully random output when acting on the state. Well, you can see that this is actually a set of measurements. And so you have a set of maximally entropic POVMs, and it's non-empty for any state. Okay, so if you give me a state, I can always find you, for instance, if you have a spin pointing z, maximally entropic POVM is measuring x, because you have probability 1/2 of getting the two possible results. Okay, this is one thing. Now, here I'm considering correlations between two particles, so we know that if one party applies a measurement, it prepares on the other particle an ensemble of states. Okay, so if you have a state rho AB, and say party A applies a measurement on state rho AB, she prepares this state rho B I, depending on her output I, and with this probability PI. Okay, this is, I guess you all know about this equation. And of course, if you have this state rho AB, for any measurement by A, this prepares an ensemble on B. And for this ensemble, we can compute the guessing probability produced by this measurement by the other party. Okay, so the party prepares an ensemble on the other party, and I can compute the guessing probability of this ensemble depending on the measurement by the other party. Okay, so now we have all the ingredients. This is the definition of this correlation measure. I look for the most distinguishable ensemble a party can prepare on the other party by making a measurement, and I demand that this ensemble is equiprobable states. Okay, so it's just I force this party to make a maximally entropic POVM with the same probabilities. She's preparing an ensemble of equiprobable states on the other side. Okay, and I maximize over all measurements by by this party. Okay, so this is maximization over maximally entropic POVMs of the guessing probability. And I put this 1 over n just because I demanded that correlation measure should be positive and 0 for product states. Okay, some of you can forget about this. It's just a convention. Okay, this is a sort of asymmetric function because it goes from A to B, but I can make it symmetric by taking the maximum of these two quantities. Okay. And now, well, I'm just telling you the ingredients. We could prove that this function is a proper correlation measure. So actually, we have a family of functions because you can do it for 2 output measurements, for 3 output measurements, for 4 output measurements, so they prepare equiprobable ensembles on the other party. And so you have different correlation measures, and you can prove that they are correlation measures. So you can prove that these functions decrease under applications of local operations. So if you want to know, maybe it sounds a bit artificial. Well, it's a bit artificial, I agree. But it also has an operational meaning, which is if Marcelo and I have a state, I care about what's the most distinguishable ensemble I can prepare by a measurement on my side. Okay, I think it has a notion of correlations built on it. I don't know what it's useful for, but it has an operational meaning. So actually, in all what I'm going to do, I will restrict to just the case in which I apply a 2 output measurement. So I'm preparing an ensemble of 2 equiprobable states on Marcelo's side. The nice thing is that this measure can be computed through the semi-definite programming. This is just a bonus point that we got. Okay, just maybe it sounded a bit obscure, but you can easily understand the correlation measure with some examples. Okay, so if the state is product, no matter which measurement this party implements and which result she gets, she will prepare the same on the other party. Okay, of course, whatever you do here, rho B1 and rho B2, you have 2 output measurements, will be equal to rho B. So you have an ensemble made of the same the 2 states are equal, so the guessing probability for you is 1/2. You make the right choice with probability 1/2, and because of this normalization condition that I chose, the value of the correlation measure is 0. So what is a maximally correlated state according to this measure? Well, a maximally entangled state, okay? Because if you have maximally entangled state, then party A can make a measurement in any basis, let's say singlet, and the measurement by Alice produces, she gets a given output with probability 1/2, and she produces two orthogonal states on the other side that are fully distinguishable. Okay, and then this guessing probability, the other party guesses the state correctly with probability 1, the guessing probability is 1, and this correlation measure takes the maximum value equal to 1/2. But again, this is a matter of correlations, not only entanglement, so it's also maximized by maximally correlated states. So if you take this state, so for the maximally entangled state, any basis, any measurement by Alice, any projective measurement by Alice produces two orthogonal states, so this maximization is sort of trivial. Here, there is a measurement by Alice in the Z basis that produces also two orthogonal states. Also, the maximization is trivial, and this guessing probability is 1, and the value of the correlation measure is also optimal. Okay, so there are already with separable states, you achieve the maximum of this correlation measure, but also with a maximum entangled state. Okay, so we are going to follow the evolution of these correlation measures to the dynamics. So this is what people usually consider for correlation measures. But I'm going to do it in a slightly more general scenario. So I'm going to have my system evolve through the dynamics. I want to study the correlation with these particles, but I will use an extra particle. So I will have a 3-particle system. I will put one of the 3 particles through the evolution, and I will monitor the evolutions between particle A and SA prime. Okay, I will do this because I want to see the difference between P and CP. This is why I will include this. Again, the same follow logics as before. If this is CP divisible, the correlations along this bipartition cannot increase because you are applying a map to these 2 particles. Okay, so I will consider this scenario where still things have to be monotonic for CP divisible evolutions. And I will study this scenario with the correlation measure I just told you. So I have to inject here, follow the correlation measure along this bipartition and see if there is a correlation backflow. Okay, but now I'm very close to my first result on distinguishability. So I will take these results and use them here. So what is the state that I use as initial state? I put the 2 states that appear in my first paper on distinguishability. There is a mistake here. Yeah, no. Yes, there is. Sorry. This should be just 0, 0, and 1, 1. So there are 2 zeros and 2 1. Forget. There should be only 1, 0, and 1, 1. Okay, so this is a state for A, and this is the state for SA prime, SA prime. Actually, this, okay, I made many typos, sorry. So this should be 0, and this should be 1, and this should be just 1, 0, and this should be 1, 1. Okay, it's just a qubit for A. This is a classically correlated qubit for A, correlated with the 2 states I use to detect the backflow on distinguishability. I hope it is clear despite of the typos. Okay, so this should be 0, 1, they are orthogonal. It's a classically correlated qubit on Alice, correlated to the 2 states I used before for the distinguishability. Well, what you can see here, that the correlation measure, if you want to study the value of our correlation measure, you should optimize over maximal entropic POVMs here. Well, I guess you will believe me if I tell you that the optimal measurement is measuring in the computational basis. It produces a random output, and is actually the optimal measurement to see, to prepare the most distinguishable ensemble on the other party. And then what happens is that this optimal measurement prepares the 2 states that give a backflow distinguishability. So because of the previous result, this also gives a backflow of this correlation measurement in this arrangement. I hope it was clear. I think it is easy. I'm not sure about my explanation, but it's easy if you understood the previous result. So here I have to put the 2 states that I was using in my previous paper, in our previous paper, and here I put a correlated qubit. Okay, so this in particular means that the result applies to all the previous cases. So for the previous case applies to all bijective evolutions. So for all bijective evolutions that are not CP divisible, I can give you this initial state that detects a backflow of correlations. And for instance, again, we learned, okay? So here, the state is separable along this bipartition. These 2 states can be, remember, they could be taken arbitrarily close one to another. So this state can be also taken arbitrarily close to a product state. So even if the amount of initial correlation is very small, you can make it as small as you want. You will see an increase in correlations for any non-Markovian evolution. And if I don't use this ancilla, well, then I won't see the difference. I won't detect anything for things that are P but not CP divisible. Okay, so it's important to add this ancilla. So what about so everything was for bijective or invertible evolutions. What about non-bijective evolutions? I was telling you that for that particular case, there are some results by Bushemian data that show backflow for distinguishability. So maybe you can play similar tricks and adapt their result to this correlation measure, okay, and do the same. So in our case, we took our results for two states, and we constructed a correlation measure. So we will wonder whether the same is possible for Bushemian data. Okay, we didn't find it. Okay, so I don't know how to do it. Okay, so I know that for non-bijective evolutions, there is an ensemble. Bushemian data told me that. I don't know how to turn any ensemble into a correlation measure. I know how to do it for two states with the same probability, with the results I told you, but for an entire ensemble, I don't know how to do it. Now, you can also, for instance, you can, however, relax the scenario, and actually, if you think about this problem, you may even consider something that I'm going to name quasi-correlation measure. Why do you demand monotonicity with this part? I mean, this part doesn't follow any evolution. Okay, so, okay, we want correlation measures because they have an operational meaning. But as a detector of non-Markovianity, it's enough to consider any function that is monotonic only by application or by one of the parties. So you can define something like a quasi-correlation measure, which is a function of a bipartite state that decreases only when one of the parties applies an operation. Again, you follow the evolution of any of these quasi-correlation measures and you see an increase, this will be a detector of non-Markovianity. But I don't like it. I like it less than having a proper correlation measure, but strictly speaking, this is also good for your purposes. And then, well, if you extend this with a quasi-correlation measure, you can easily find a function that detects any CP non-divisible evolution. Okay, and this is something, you have to use something called singlet fraction fidelity. Okay, this is a definition which is not the standard one, and it's not the one I'm used to. It was given in this paper by Koenig, Renner, and Schaffner. So they defined a singlet fraction fidelity of a given state, rho SA, as the maximization of the overlap of your state with the maximum entangled state optimized over operation by one of the parties. So usually I tend to think about singlet fraction fidelity as optimization with respect to operations by the two parties. For some reasons, they just took this maximization over one party. It's very easy then to prove that this function is monotonic under operations by one of the two parties. Okay, so this function cannot increase if S applies a map. Okay, it just follows by definition. And in the same paper, they proved that this function, whenever you have a state like the one I'm giving you here, so I have pi, rho I correlated with the classical information on the other party, this single fraction is equal to the guessing probability of this ensemble. Okay, then it's trivial. Okay, so you follow the evolution of this quasi-correlation measure for this initial state, and you put here the ensemble by Bushemian data, this quasi-correlation measure will show an increase of distinguishability of correlations. It's a bit of cheating, I must say, but for quasi-correlation measures, you can always do that. And actually, this singlet fraction is not a correlation measure. Okay, so it's either easy to prove that this increases when A applies an operation. Okay, so you cannot have any hope of transforming this into a proper correlation measure. Okay, so went faster than expected, but this is good for our dinner plans. So I will conclude, okay? So I was telling you about different things. Remember, our motivation was to connect a definition of non-Markovianity which makes sense, and I would say it's more formal or mathematical, which is CP divisibility, failure of CP divisibility, with other notions that perhaps are more operational, which is backflow detected by an operational quantity, such as distinguishability of correlation measures. So for distinguishability, we gave a recipe. So you have a situation where things are not CP divisible and things are invertible. I gave you a very simple recipe of families of states for which you will see an increase of distinguishability. These are two states with the same probability that can be separable and even arbitrarily close to each other. Then I moved to correlations, and I proved that we proved that entanglement and mutual information failed to detect all Markovian effects, understood as failure of CP divisibility. But then I proved you that there are correlation measures satisfying this property, and I gave you one which is based on this preparation of an ensemble of distinguishable ensembles by one party into the other. then from the pre-results, since I was using the pre-result, these results here imply that the initial state is separable and can be arbitrarily close to a product state. So just to see a backflow. Any amount of initial correlation is enough to see a backflow. What is also interesting about this correlation measure is that to see all non-CP dynamics, I have to enlarge the up to now study scenario, and I have to put S, A, and an extra auxiliary particle, A prime. And then I show you that if you even enlarge more the scenario and you only care about quasi-correlation measure, it's very easy to prove that you will see any backflow. So in a way, you can see that these two things actually if and only if. Okay, there are some things perhaps if you want to make these things this connection. So again, this should be no. Okay, so there's a mistake here. So CP divisibility implies no distinguishability backflow, but also it goes in the opposite direction. So I think there are some questions that are worth understanding. So I would like to see a construction of an ensemble for non-bijective evolutions. There are some cases, some relevant, physically relevant changes that are non-bijective. So up to now, we only have the result by data that tells us that there is an ensemble, but we don't know how to find it. And the same, I mean, in the case of correlations, I presented you a correlation measure detecting backflow, but if now you ask me about non-bijective evolutions, I don't know how to do it. So we don't have any measure in that case. And I think something that is also worth understanding is I was sort of, in a way you could say that I was cheating, because the example for the mutual information that I was giving you that fails to detect, to show backflow in the mutual information was actually P divisible. Okay? And with the measure I introduced you to detect the difference between P and CP divisible, I have to add an extra ancilla. So it's interesting to understand whether this also gives an advantage for mutual information. I don't know. Okay, so I think enlarging this scenario with an extra particle and looking at correlations between what I say A and S and A prime, we can go back to mutual information entanglement and study this measure in this enlarged scenario. Okay, I think this is open, and I would like to understand better what's going on there. Okay, and, thank you very much.
Questions?
Thank you. Very nice talk, Tony. What about the Pearson correlation function, like statistical correlation function?